Hello everybody, this video clip is the second video clip for chapter 6 and we still in section 6.1. Actually this section is just simply to remind you about the definition of the derivative of a function and also will justify all the properties or formula that you have learned from your math 1 and sometime in math 2 as well. Okay, so for example, last video clip we already talking about the product rule and the quotient rule. For this video clip, we are going to talk about the chain rule. Okay, however, before we go into the chain rule, we need this important tool first, which is so-called the Theodoris theorem. Okay, so if we let your f again as a function from the interval I to r, okay, and your c it is inside that interval, then your f is differentiable at this particular point c if and only if you can find a function phi from the same interval I to r that is continuous, okay, only continuous at the point c, and your fx minus fc equals to phi x times x minus c. So actually, I mean, of course, if roughly speaking, it seems that your phi it is f of x subtract f of c over x minus c. So roughly speaking, your phi x almost look like the quotient that determine your f prime, right? However, because this one your c it is inside this interval, so you can write this kind of quotient in uh, uh, only in the case that your x is not that point c, right? And actually in this case, if you can find this kind of function phi that is continuous, then this phi at c, okay, it is actually your f prime at c. For example, if you consider your fx equals to x to the power 7, we can see from the factorization that your x raised to the power 7 minus c to the power 7, it is equals to x minus c, and then x to the power 6, c x to the power 5, c square x 4, c cube, oh, I'm sorry, this one should be x cube, okay, and then c 4x square, and c 5x, and c raised to the power 6, okay. So it means that your this one, okay, it is actually your f of x minus f of c, right? Okay, and this one it is equals to x minus c with this polynomial. So of course this polynomial it is continuous immediately, so we can regard this one as your phi of x. Okay, so your phi of x, okay, can be x6 c x5 c square x4 c cube x cube c4 x square c5x and c6, okay, which is of course, I mean, if we take your phi at c, so you got c raised to the power 6 add up together for 7 terms, right? For 7 terms. So it means that you have f prime, which is your phi at c as 7c6, okay, for all c in a real number, okay. So let us try to do the proof of this theorem, okay. However, this theorem it is the if and only if, so you need to do both way, okay. Let us do the p implies q first, okay. So of course, I mean, this assertion you are going to assume that your f is differentiable at the point c, okay, and we are going to define, as I told you, because your phi look like this quotient. However, this quotient valid whenever your x is not c, so we are going to define, because you are going to find this phi, right? So your phi can be simply this quotient, okay, because this is what we need, right? However, this one it is okay whenever your x is not c, and then because your f is differentiable, then it means that your f prime as c exists, right? So you can just simply define your phi as your f prime as c when your x is equals to c itself. Okay, so of course immediately the limit as your x goes to c of your phi x, okay, because this one, it is the one that your x is not equals to c, it will be equals to the limit of this quotient fx over fc minus fc over x minus c, okay. However, because your f is differentiable, okay, and usually we abbreviate like this, okay, f is differentiable, then it means that this one, the limit exists and it is equals to f prime as c, which is phi c. So it means that your phi is simply continuous at the point c, okay. And if you let, I mean, so we have the first property of the phi, right, that your phi must be continuous. We are going to look at the second property. So look at x in I, okay. So we know that if your x equals to c, then your phi c of course equals to f prime c already, and your fc minus fc, it is equals to fc and c minus c, because this one it is 0, this one is also 0, right? Okay, so we got this equation. However, if your x is not c, okay, your phi x, it is already defined by this quotient. So which means that, I mean, you can just simply do the cross multiply to have your fx minus fc equals to phi x and x minus c, okay. So it is done, right, for the first assertion. Let us look at the other way around. If you assume the q and to try to prove the p, okay. So let us assume that there exists a function phi from the same interval, okay, that continuous at the point c, and have this kind of property that your fx minus fc equals to phi x minus c for all x in I. We are going to prove that your f, okay, right here is actually differentiable at the particular point c, okay. So of course, I mean, as I told you that this equation actually look like the quotient determine your f prime. However, you need to take away the c. So if you take away the c, this one can be written as this quotient, okay. And because your phi is continuous at c, so what does this mean? The limit of phi x as your x goes to c, it is the phi itself. So it means that the limit as your x goes to c of this quotient fx minus fc over x minus c, because this quotient your on your left hand side, it is actually your phi, right? So this limit exists, right? And it is not only exist, and it is equals to your phi as c, right? So it means that your f is differentiable because the limit of this quotient exists, and immediately your f prime as c, it is actually your phi c as we need. Okay, so this is the proof of the Carathéodory's theorem. All right, now we are ready to establish the chain rule. Okay, so for the chain rule, don't forget that we have your f, okay, from j to a real number r. Okay, so your f look like this. Okay, and then your g, okay, from the j to from I, okay, which is a little bit greater than f of j to r as well. Okay, this is your g. All right, and then here is your GOF. Okay, so from the chain rule, okay, as you learned before, it is saying that a derivative of this composite function at the point C, I mean if your f is differentiable at C and your g is differentiable at your FC, okay, this one it will be defined, I mean the GOF is differentiable and it is equals to the derivative at this point, it is equals to g prime at FC multiplied by f prime at C. Okay, so of course, I mean we already have the Carathéodory theorem, right, which is saying that if your f is differentiable at the point C, we can find the phi, okay, from the same domain, okay, so that your f of x minus f of c equals to phi of x multiplied by x minus c, right? Okay, for each and every point x in the domain of the function x, of the function f, and this phi is actually your f prime as c, right? I mean the value of phi as c is actually your f prime as c. We are going to of course use this one. However, we have two differentiable function, okay, not only the f but also the g, so it means that we are going to use this Carathéodory theorem twice. Okay, so let us try to prove it. Okay, so because your f is differentiable, of course there exists a phi, as I told you, okay, from j to r, okay, so that your phi is continuous at the point C, and your f of x minus f of c equals to phi x and then x minus c. Okay, so let me rewrite it here. All right, okay, you got this thing for all x in j. Okay, and of course your phi c, it is the same as f prime as c. All right, this is what we have previously. How about your g? Your g is differentiable as well. However, your f, it is differentiable at c, but your g, it is differentiable at fc. Okay, so by the same Carathéodory, okay, we have another function. Instead of using phi, okay, we use the sign. Okay, this sign, okay, define from I to R, okay, because the domain of G is I. All right, so that your psi is continuous at GC, FC, right, at the point of differentiable, and your g, okay, let's say actually we should have g at x, right? However, instead of using the same parameter x, we use g of y, and then g at this differentiable point, okay, it will be equals to sine of y, and then y minus the point of differentiable. Okay, so of course this one it is for all y in I, right? And don't forget that psi prime, psi at the point of differentiable, it is the same as g at g prime at this point. Okay, it is the same as g prime at this point. So let's look at your f, okay, for all, because your f of j, it is the subset of I. So this one is the range of function f, right? Okay, so it means that for all x in j, okay, this is the one of the assumption, right? Remember here, right here, f of j, it is a subset of I. So for each x in j, your f of x, it is actually in I, right? So your f of x can be regarded as one of the parameter y in the interval I, okay? So it means that your g of f of x minus your g at fc must be equals to psi at f of x minus f of x minus f of c. Okay, this one for all x in the interval j. All right, so what is this expression? It is actually a composite between g and f at the point x. This one, it is a composite of g and f at the point c. Sorry, so this one, it is a psi of f of x, and then what is your fx minus fc? It is right here, right? Fx minus fc, it is a what? Phi x minus c. All right, okay, so this one can be regarded as another function, right? This one, okay, can be regarded as another function for the Carathéodory theorem, because your psi, okay, actually your psi of f of x is continuous at the point x equals to c. Your phi is also continuous at the point x equals to c as well. All right, so the multiplication, the product of these two functions is continuous at the point x equals to c. Okay, and your difference of two function, okay, by two function it means the GOF at x and the GOF at c, the difference among these two equals to this function multiplied by x minus c. Okay, so it means that by this theorem, okay, we can conclude that your GOF is differentiable at the point C, and the GOF prime, it is actually the function value, okay, this function value, right, this one, as you replace your x by c. However, as you replace your x by c, you see the sign of f of x, it is g prime, the sign of f at c, it is a g prime at fc, and phi at c, it is actually your f prime at c. All right, so we have this one, the composite derivative, it is equals to a derivative of g evaluated at fc multiplied by a derivative of f evaluated at x equals to c. All right, okay, so this is the chain rule that you have learned, okay, and this is how you prove it using Carathéodory theorem twice. The next theorem is something that you may have been used during your math one, but you may forget, okay. For example, the formula in math one that you have will look like this, okay, that your dy by dx, it is the same as 1 over dx by dy. So for example, if your y is a function of x, okay, but instead of writing as y equal, you may have x equals to y square over y cube plus 1, something like that, and you need to find your dy by dx, okay, then you can just use this formula to find your dx by dy instead, okay. With, I mean, for this one you need to use the quotient rule, and then the answer will be in terms of y, okay, will be in terms of y, something like that. So it's like quite similar to the implicit differentiation, okay. However, this kind of implicit, it is depends on the function itself, I mean the function and the inverse of the function itself. So for this one, you have your f, okay, as a function from I to a real number r, which is strictly monotone, okay, and continuous on I, okay. For, I mean, the strictly monotone, it means that it is either increasing or decreasing, okay, I mean only one way, okay, and it is continuous on the interval I, and you let your your g to be a function from the range of f to the real number, which is again strictly monotone, and continuous, which is a continuous inverse of f, okay. So actually your g is an inverse of the function f, okay. If your f is differentiable at the point c in that interval I, and your f prime c is not 0, then the inverse of that f is also differentiable at the same point fc, okay, and your g prime at fc, it is actually 1 over f prime c, or it is f prime at g of fc, because don't forget that the composite of g and f right now, because your g is the inverse of f, right? So this one is look like f inverse composite f at c, so the inverse and the f will cancel, and you get only the one inside there, okay. So again, because this one follow from your chain rule and also the Carathéodory theory, we are going to use that theorem again. So let us start our proof, okay. So we just let this point c that we need to talk about a derivative, okay. So if we have this point c in the real number, by the Carathéodory theorem, okay, we know that there will be the phi, okay, which is from I to R, that is continuous, okay. So this phi came from what? Came from your f is differentiable at this point c, right? Okay, so this phi, because of this, okay, we have the continuous function phi at c, and this difference fx and fc equals to phi of x and x minus c for all x in the domain I. Okay, and of course your phi at c, it is actually f prime at c, and your f prime at c right now is not equals to 0, so this one is not equals to 0. All right. Next, because of this assumption that your f prime at c is not a 0, and actually your phi is continuous, okay, so this one, it means that there will be a neighborhood of c, okay, which is sometimes we call a delta neighborhood. So we have a delta greater than 0 such that your phi of x, okay, is not 0 for each and every x in this neighborhood, and of course this neighborhood must be inside the domain I. Okay, so from that C and then to the left and to the right a little bit, okay, this phi of x is not equals to 0. So we let U, okay, to be the image of this neighborhood, okay, which is C minus delta and C plus delta, but then within this domain, then this inverse, okay, which we call the G, will satisfy the property saying that your F composite G, okay, the F and the F inverse, as you attach it together by composite, it will give you the one inside, all right, for each and every y in U. Okay, and we are going to use this property, right? We are going to use the property that we established over there, okay, but we need to get involved the G, all right, we need to get involved the G. So if we talking about order y, okay, which is in U, then your y is actually the f of gy, right? So we can start with, I mean, and your, don't forget that your f is sorry, your U is the image of your f under this neighborhood, right? So it means that if your y, it is inside this U, then it means that actually your gy, okay, it is inside this neighborhood. All right, so this gy, it is actually inside this neighborhood, okay, and within this domain I. All right, so it means that your gy can replaced, I mean your x can be replaced, your x here, because all the x, it is all the element in the domain, right? This x right here can be replaced by this gy, because your gy is also one of the element here. So your f of gy minus f at c, okay, however your f at gy from this equation, it is the y itself minus f at c, okay, and from this relation we got phi of the same point here, you see f at x and phi at x, but right now your x replaced by gy, so this one, it is your phi at gy, and then this one is x again, but your x is replaced by gy minus c, but in order to make your c involve the g, you can put it as g of f of c, okay, because of the inverse property. When you have your g and your f together like this, it is actually equals to the c itself. Okay, so this is what we actually need, right? on this side, you see gy and g at this particular point equals to the point that it is input here in the g, and also the point that input right there on the g. Is that correct? However, by the Carathéodory theory, okay, if we are going to use the difference of the function here, okay, you are going to have one continuous function multiply with a difference of the input of these two function value, right? However, this time your continuous function is right here, multiply with your function value g at y and g at f of c. So if you really need, you can just divide it, right? So it means that your gy minus g at f of c will be 1 over phi of gy, and then multiply by y minus f at c. Okay, and this one we can do the division, because don't forget that this phi, okay, is not going to be 0, right, in this neighborhood, and your gy, it is in this, really in this neighborhood, so this one is not going to be 0. So this particular function, it is actually continuous at your point fc. This is because your phi of g at this particular point, okay, because your f and your g is inverse of each other, so what you end up with is the phi c, okay, and this phi is continuous at this point c, and it is not 0, okay, as we assumed before. So this one, it is actually continuous at this particular point fc, okay, the 1 over. So what does this mean? We got a difference of a function value equals to one continuous function multiplied by the difference of the input of these two function value. So it means that by, again, the Carathéodory theorem, okay, we have that your g prime at this particular point exists, right, and actually your g prime at this point, it is this function at the same point value, right? So it's 1 over phi of g of f at c. Okay, however, what is your actually this one is a phi at c, right? Because again your g and your f, they are inverse of each other. But what is your phi? Your phi at c, it is actually your f prime at c. So we got 1 over f prime at c, right? So we have g prime at this point equals to 1 over f prime at the same point c as required. Okay, so we have this one as the about the the derivative of the inverse function. Okay, so we don't really need to find the inverse of the function, but we can use this property to find a derivative of its inverse. All right, so all these are something that you have learned in your math 1 and you have used it, okay, but we just justify it in this section. So for the next section, we are going to go a little bit further beyond what you have learned in your math 1, and then to see whether we can apply all that thing to something that you have learned before as well. Okay, so we'll see you then. Bye bye.